Do me a favor. Right now, wherever you are, just wiggle your pinky finger. Go on, just give it a little wiggle. Curl your toes. Feel that. Simple, right? You think wiggle finger and it wiggles? You think curl toes and they curl? It feels instantaneous, like magic. But what if I told you that, in that split second, you initiated one of the most complex, high-speed, and utterly miraculous processes in the known universe? You sent a message from the CEO in your head, down a superhighway of incomprehensible complexity, to a tiny muscle at the farthest edge of your body, and it all happened faster than you could blink. That's superhighway. That's what we're here to talk about. It's not your brain. Your brain gets all the credit, all the headlines. It's the rock star, the celebrity, the one everyone talks about. But the brain would be a king without a kingdom, a genius locked in a silent, dark room, if it weren't for its partner. Its lifeline. The unsung hero of your nervous system. The spinal cord. For the next while, we are going on a journey. A deep dive into this incredible structure that you carry around inside you every single day, but probably never think about. We're going to explore the anatomy of the spinal cord and the vast network of nerves that branch off from it, like the intricate root system of a colossal tree. And I promise you, by the end of this, you will never think about wiggling your finger the same way again. You'll have a newfound respect, a sense of awe, for the biological marvel tucked away inside your own backbone. So, what is the spinal cord, really? Forget the dry textbook definitions for a moment. Picture a central command hub, a bustling grand central station of information. Every single second of your life, millions upon millions of signals are zipping up and down this structure. Information from your skin about the temperature of the air, the texture of your clothes, it's the gentle pressure of the chair you're sitting in. All of that is screaming up the spinal cord to your brain. It's sensory data. It's the input. At the exact same time, your brain is sending messages back down. Commands, orders, breathe in, shift your weight. Reach for that cup of coffee, maintain your balance. That's the motor data, the output. And the spinal cord is the master conductor of this entire orchestra. It's the ultimate middleman, ensuring messages get where they need to go, at speeds that are almost impossible to comprehend. We're talking up to 268 miles per hour. It's faster than a Formula One race car. But it's even more than a simple highway. It's not just a passive cable. The spinal cord has a mind of its own in a way. It can make its own decisions, lightning-fast executive orders that don't even need the brain's approval. Have you ever touched something dangerously hot and yanked your hand away before you even consciously registered the pain? You didn't think, oh, that stove is hot. The heat is causing damage to my skin cells. I should probably activate the muscles in my arm to retract my hand. No, your hand was already gone. That was your spinal cord. That was a reflex arc, a life-saving shortcut that we will be exploring in incredible detail later on. It's a built-in emergency response system that bypasses the head office to save you from harm. So in this series, we're going to peel back the layers, literally. We'll start with the incredible armor that protects this vital structure, the bony fortress of your spine. Then we'll look at the delicate wrappings that cushion it, a system so elegant it's like biological bubble wrap. After that, we're going into the cord itself, exploring its internal geography. The mysterious gray matter and white matter that you've probably heard of but never really understood. We'll map out the major pathways, the northbound lanes carrying information to the brain, and the southbound lanes carrying commands back down. And finally, we'll follow the nerves as they branch out from the cord, spreading to every single corner of your body, creating the network that allows you to experience and interact with the world. This isn't just an anatomy lesson. This is the story of you. It's the story of how you feel, how you move, and how you survive. It's the story of the silent, tireless hero working 24/7 to keep the whole show running. So get comfortable. Let's begin our journey down the information superhighway. Let's explore the anatomy of the spinal cord. All right, so we've established that the spinal cord is ridiculously important. It's the main communication line between your brain and, well, everything else. If something is that critical, you can bet that nature has spent millions of years figuring out the absolute best way to protect it. You don't put the crown jewels in a cardboard box, and you don't house your central nervous system in something flimsy. The spinal cord is protected by a multi-layered biomechanical fortress that is a masterpiece of engineering. Let's start with the most obvious layer of defense, your backbone, the vertebral column. When you run your hand down the middle of your back, those bumps you feel are parts of your vertebrae. We tend to think of it as one single spine, but it's not. It's a brilliant, flexible stack of 33 individual bones. Think of it like a stack of intricately shaped, super strong Lego bricks, all interlocking perfectly. This segmentation is key. If your spine were one long, solid bone, you wouldn't be able to bend, twist, or move. You'd be as stiff as a board. The stacked nature of the vertebrae gives you that incredible range of motion, while still forming a solid protective casing. These vertebrae aren't all the same either. They're specialized for their location. Up top, in your neck, you have the 7 cervical vertebrae. They're smaller, more delicate, because they need to allow for the fine movements of your head. They're all about mobility. Then you have the 12 thoracic vertebrae in your mid-back. Each of these connects to your ribs, forming the sturdy rib cage that protects your heart and lungs. These guys are all about stability. Below that are the 5 massive lumbar vertebrae in your lower back. These are the heavy lifters. They're thick, chunky, and built to withstand the enormous pressure and weight of your entire upper body. They're all about strength. Finally, you have the sacrum and coccyx at the very bottom, which are fused vertebrae that form the back of your pelvis. Now, here's the clever part. Each one of these vertebrae has a hole in the middle, called the vertebral foramen. When you stack all 33 of them up, these holes align perfectly to create a long, continuous tunnel. This is the vertebral canal. And it is inside this bony, heavily fortified tunnel that the delicate spinal cord resides. It's like a precious fiber optic cable running through a secure underground conduit. It's protected from bumps, knocks, and the general stresses of everyday life. Between each vertebra, you also have an intervertebral disc, which acts as a shock-absorbing, gelatinous cushion. So every time you jump, run, or even just walk, these discs compress and absorb the impact, protecting both the bones and the precious cord inside. But the protection doesn't stop there. Bone is great, but it's hard and unforgiving. If the spinal cord were just rattling around inside that bony canal, it would get damaged. So, nature added a series of sophisticated soft tissue layers for cushioning and support. These are called the meninges. You have them around your brain, too. Think of them as a 3-layered high-tech sleeping bag for your spinal cord. The outermost layer is called the dura mater. Dura mater is Latin for tough mother, and that's exactly what it is. It's a thick, leathery, incredibly durable sac that encases the entire spinal cord. It's the heavy-duty, waterproof outer shell of the sleeping bag. It's the first line of soft tissue defense. Just inside the dura mater, you have the next layer, the arachnoid mater. Arachnoid means spider-like, and it gets its name because below it are these thin, wispy, web-like fibers that reach down to the next layer. This web-like space is called the subarachnoid space, and this is where the magic happens. This space isn't empty. It's filled with a special crystal clear fluid called cerebrospinal fluid, or CSF. The CSF is, without a doubt, one of the coolest substances in your body. Your spinal cord is literally floating in it. It's a hydraulic cushion, a liquid shock absorber. If you get a jolt, the fluid disperses the force, preventing the delicate cord from slamming into the hard bone of the vertebrae. It also provides nutrients to the spinal cord and removes waste products. It's a combination of a flotation device, a shock absorber, and a personal chef and garbage disposal service, all in one. Finally, pressed right up against the spinal cord itself is the third and innermost layer, the pia mater. Pia mater is Latin for tender mother. It's an incredibly thin, delicate membrane that shrink wraps the cord, following every single tiny groove and contour. It's like a gentle, loving hug, holding everything together. It's rich with blood vessels that help supply the spinal cord with oxygen and nutrients. So, let's recap the security system. We have a flexible column of 33 interlocking bones, cushioned by shock-absorbing discs, forming a fortified tunnel. Inside that tunnel, the spinal cord is wrapped in 3 protective membranes: the tough outer dura mater, the web-like arachnoid mater, and the delicate inner pia mater. And between 2 of those layers, it's floating in a bath of cerebrospinal fluid, cushioning it from any and all impact. That is an absolutely extraordinary level of protection. It's a fortress of bone and fluid, all designed to protect the most important communication highway in your body. Now that we know how it's protected, it's time to venture inside that fortress. Next, we're going to look at the internal structure of the spinal cord itself, the mysterious and beautiful world of gray and white matter. All right, we've made it through the fortress. We've navigated the bony vertebrae, the shock-absorbing discs, the tough dura mater, the fluid-filled arachnoid space, and the delicate PA mater. We are now, metaphorically speaking, inside the spinal cord itself, and what we find here is not just a simple cable. It's a structure of profound complexity and strange beauty. If you were to take a cross-section of the spinal cord and look at it under a microscope, you would see one of the most iconic and important shapes in all of neuroanatomy, a butterfly. Right in the center of the spinal cord is a butterfly-shaped or H-shaped region of darker tissue. This is the famous gray matter. Surrounding it, filling out the rest of the oval shape of the cord, is the lighter-colored white matter. This distinction isn't just for looks. It's the fundamental organizational principle of the spinal cord. It separates the processing centers from the communication highways. Let's talk about the gray matter first, the butterfly. Why is it gray? It's gray because it's primarily made up of the cell bodies of neurons. Think of the neuron as a little tree. The cell body is like the root ball in the base of the trunk. It's the neuron's life support center. It's containing the nucleus and all the machinery to keep the cell alive and functioning. The gray matter is also packed with dendrites, the tiny, dull, branch-like extensions that receive signals from other neurons in the very beginning and end points of axons, which are the long cables that transmit signals. It's also filled with glial cells, which are the support staff of the nervous system. So, if the gray matter is full of cell bodies and connection points, what is its job? Its job is processing. The gray matter is where the thinking of the spinal cord happens. It's where decisions are made. It's like the bustling city centers on our superhighway analogy. It's where the signals arrive, get sorted, rerouted, and where new signals are generated. When that sensory signal from your fingertip touching a hot stove comes in, it's the gray matter where that signal is received, and where the command to pull your hand away is instantly generated. It's the integration center. This butterfly shape isn't random either. It's highly organized. The wings of the butterfly are called horns. The horns pointing towards your back are called the dorsal or posterior horns. These are the receiving docks. They primarily receive sensory information coming in from the body. So information about touch, pain, temperature, it all arrives at the dorsal horns. The horns pointing towards your front are the ventral or anterior horns. These are the shipping departments. They contain the cell bodies of motor neurons, the nerves that send out commands to your muscles, telling them to contract. So, the signal to wiggle your finger originates from the cell bodies in the ventral horns. In some parts of the spinal cord, there are also little bumps on the side called lateral horns, which are involved in the autonomic nervous system, the stuff you don't consciously control. It's like heart rate and digestion. So, that's the gray matter. The central processing unit, the city centers, shaped like a butterfly. What about all the stuff surrounding it, the white matter? Why is it white? It's white for a very specific and crucial reason, myelin. Myelin is a fatty lipid-rich substance that wraps around the axons of neurons like insulation around an electrical wire. You see, the gray matter has the cell bodies, but the axons, the long-distance transmission cables, have to travel up and down the spinal cord to connect with the brain or with other levels of the cord. These axons are bundled together in the white matter. The high-fat content of the myelin sheath gives this tissue its pale, whitish appearance. Myelin does two incredibly important things. First, it insulates the axon, preventing the electrical signal from leaking out, just like the rubber on a power cord. Second, and this is the really genius part, it dramatically speeds up the nerve impulse. The signal doesn't travel smoothly down the axon. It actually jumps from gap to gap in the myelin sheath. This process, called saltatory conduction, is what allows signals to travel at those mind-boggling speeds we talked about earlier. Without myelin, your movements would be slow, uncoordinated, and your sensations delayed. The white matter isn't just a random jumble of wires either. It is meticulously organized into columns, or funiculi. And within these columns, the axons are bundled together into what we call tracts. Think of these tracts as the individual lanes on the superhighway. Just like a highway, there are northbound lanes and southbound lanes. The northbound tracts are the ascending tracts. They are made of sensory neurons carrying information up to the brain. There are specific tracts for carrying pain and temperature information, others for fine touch and proprioception, your sense of where your body is in space, and so on. They are the reporters, sending field data up to headquarters. The southbound tracts are the descending tracts. They're made of motor neurons carrying commands down from the brain. These tracts control everything from the voluntary contraction of your biceps to the involuntary adjustments in your posture that keep you from falling over. They are the messengers, delivering orders from the CEO. So, you have this beautiful, elegant system. Sensory information comes in from your body, enters the spinal cord, and is delivered to the dorsal horn of the gray matter butterfly. There it might be processed for a quick reflex, or it might be sent on to an axon and an ascending tract in the white matter to travel up to the brain. The brain then makes a decision and sends a command down a descending tract in the white matter. That signal then synapses with a motor neuron in the ventral horn of the gray matter, which then sends the command out to the muscle. It's a constant, dynamic, perfectly coordinated dance of electrical and chemical signals, and it's all happening inside you right now. The butterfly and the highway. The processing and the transmission. The gray and the white. This internal geography is the key to everything the spinal cord does. Next, we'll see how the information actually gets on and off this highway by exploring the spinal nerves themselves. So, we've built the fortress that protects the spinal cord. And we've explored its internal landscape, the gray matter processing hubs, and the white matter communication highways. But a highway is useless if there are no on-ramps or off-ramps. How does the information from your big toe get onto this superhighway? And how do the commands from your brain get off the highway to actually make that toe move? The answer lies in the spinal nerves. These are the peripheral roads, the local streets, and the driveways that connect every single part of your body to the central superhighway of the spinal cord. And there are a lot of them. Emerging from the spinal cord in between each pair of vertebrae is a pair of spinal nerves, one on the left and one on the right. Total, you have 31 pairs of these nerves. They are the physical link between your central nervous system, the brain, and spinal cord. In your peripheral nervous system, everything else. These 31 pairs are neatly organized and named according to the region of the vertebral column they emerge from. You have 8 pairs of cervical nerves in the neck, labeled C1 to C8, 12 pairs of thoracic nerves in the chest area, T1 to T12, 5 pairs of lumbar nerves in the lower back, L1 to L5, 5 pairs of sacral nerves in the pelvic region, S1 to S5, and finally 1 tiny pair of coccygeal nerves at the very bottom. This numbering system is incredibly important, not just for anatomists, but for doctors. If a patient comes in with numbness or weakness in a specific part of their body, a doctor can use their knowledge of which spinal nerve serves that area to pinpoint exactly where the problem might be along the spinal cord. It's like a wiring diagram for the human body. Now, here's where it gets really elegant. Each spinal nerve isn't just one big cable. As it gets closer to the spinal cord, it splits into 2 distinct branches, called roots. This is the secret to the spinal cord's incredibly organized, 2-way traffic system. You have a dorsal root towards the back and a ventral root towards the front. And they are strictly one-way streets. The dorsal root is the on-ramp. It's purely sensory. It carries all the incoming information to the spinal cord. The feeling of a cool breeze on your skin, the pain of a paper cut, the stretch in your muscles when you reach for something, all of that information travels along a sensory neuron. It enters the spinal nerve and flows exclusively through the dorsal root to connect with the dorsal horn of the gray matter butterfly we talked about. There's a distinctive bulge on every dorsal root called the dorsal root ganglion. Ganglion is just a collection of neuron cell bodies outside the central nervous system. In this case, it contains the cell bodies of all the sensory neurons. You can think of it as a security checkpoint or a ticket booth on the on-ramp, where all the incoming sensory data is logged before it enters the main highway. The ventral root, on the other hand, is the off-ramp. It is purely motor. It carries all the outgoing commands away from the spinal cord. After the brain sends a signal down a descending tract, and after that signal is processed in the ventral horn of the gray matter, the new command to say, contract your quadriceps muscle, travels out through the ventral root. It's a one-way street for outgoing traffic only. So, picture it. Sensory signals in, motor signals out, in through the back door, out through the front door. This strict division of labor is called the Bell-Magendie law, and it's a fundamental principle of how your nervous system is wired. Just outside the spinal column, the sensory dorsal route and the motor ventral route merge together. They join to form the single, mixed spinal nerve. It's called a mixed nerve because now, in this one cable, you have both sensory fibers on-ramp traffic and motor fibers off-ramp traffic, traveling alongside each other. It's like a two-way street. This single spinal nerve then travels out into the body. But it doesn't just go to one place. Soon after emerging, it branches out again and again, getting smaller and smaller, heading to specific destinations. Some branches will go to the skin to pick up sensory information. We call these cutaneous branches. Other branches will go to the muscles to deliver motor commands. Some will go to the deep muscles of the back and the joints. This intricate branching pattern is how a single nerve emerging from your neck can be responsible for both the feeling in your thumb and the contraction of your bicep. So, the system is beautifully simple in its concept, yet infinitely complex in its execution. 31 pairs of on-ramps and off-ramps connecting the central highway to the entire country of your body. Each ramp is meticulously organized into one-way routes, a back door for sensory input and a front door for motor output. These routes then merge to form a mixed two-way street that branches out to serve every muscle and every patch of skin. This is the physical wiring that makes sensation and movement possible. And it's this very wiring that allows for one of the most spectacular features of the spinal cord, its ability to act on its own, to make split-second decisions without bothering the brain. Next time we are going to explore the high-speed emergency system known as the reflex arc. We've talked a lot about the brain as the CEO and the spinal cord as the superhighway for its messages. But what happens in an emergency? What happens when there is no time to send a report all the way up to the head office? Wait for a decision, and then get the orders back down? In a true crisis, waiting for that round trip, even at 268 miles per hour, could be the difference between a minor injury and a catastrophic one. This is where the spinal cord reveals its most impressive trick. It can take charge. It has its own built-in, lightning-fast emergency response protocol. This is the reflex arc. The classic example, the one we all know, is touching a hot stove. But let's break that down, step by step, to see the sheer elegance of this system. It's a 5-part journey that happens so fast it feels like one single event. Step 1 is the receptor. In your fingertips, you have specialized nerve endings called nocestors, which are designed to detect pain and temperature extremes. They are the silent sentinels, constantly monitoring the environment. The moment your finger touches that dangerously hot surface, these receptors fire off an alarm. They convert the physical stimulus of heat into an electrical signal. The fire alarm has been pulled. Step 2 is the sensory neuron. This is the first responder. The electrical alarm signal generated by the receptor zips along the axon of a sensory neuron. This neuron's axon is a long cable that travels from your fingertip, up your arm, to the spinal cord. It enters the spinal cord through the on-ramp. We talked about the dorsal root. Remember, the dorsal root is for incoming sensory information only. This is the emergency call heading straight for the local precinct, not the federal headquarters. Step 3 is the integration center. This is where the magic happens. This is the crucial shortcut. The sensory neuron doesn't immediately travel up the white matter to the brain. Instead, right there in the gray matter butterfly of the spinal cord, it passes its message on. In the simplest reflexes, it might talk directly to a motor neuron. But in a pain reflex like this one, it usually talks to a tiny middleman called an interneuron. An interneuron is a neuron that lives entirely within the central nervous system. It's like a local dispatcher. Its job is to receive the emergency signal from the sensory neuron and immediately make a decision. The decision is simple. This is a major threat. We need to move now. Step 4 is the motor neuron. The interneuron, our dispatcher, instantly activates a motor neuron. The cell body of this motor neuron is sitting right there in the ventral horn of the gray matter, the shipping department, as soon as it gets the go. Signal from the interneuron, it fires its own electrical impulse. This is the evacuation order. Step 5 is the effector. The axon of the motor neuron travels out of the spinal cord through the ventral root, the off-ramp for motor commands. It speeds down your arm and connects to the effector, which in this case is your bicep muscle. The signal from the motor neuron tells your bicep to contract and contract violently. This contraction pulls your lower arm up, yanking your hand away from the hot stove. And all of this receptor, sensory neuron, interneuron, motor neuron, effector happens in a fraction of a second. Your hand is already moving away from the source of pain before your brain even knows what's going on. Think about that. The conscious sensation of pain, the ouch, that's hot. Feeling's a separate message. While the interneuron was activating the motor neuron to save your hand, it also sent a signal up an ascending tract in the white matter towards your brain. But that message has a longer journey. It has to go all the way up the spinal cord, get processed in various parts of the brain, and finally reach your conscious awareness. By the time your brain registers the pain, your spinal cord has already taken executive action and saved you from a much more severe burn. Your brain is the last to know. It's like the CEO getting a damage report about a factory fire, only to be told in the same breath that the local fire chief has already put it out. This is not just for pain. Think about the Negerk reflex a doctor tests with a little rubber hammer. Tapping that tendon just below your kneecap stretches your quadriceps muscle. A stretch receptor in the muscle fires a signal up a sensory neuron. In the spinal cord, that sensory neuron talks directly to a motor neuron, which immediately sends a signal back to the quadriceps, telling it to contract. This makes your leg kick out. It's a two-neuron reflex even faster than the pain reflex. Its purpose is to help you maintain posture and balance. If you start to sway, your muscles stretch, and the reflex instantly contracts them to pull you back, preventing a fall. The reflex arc is a fundamental survival mechanism. It is hardwired efficiency. It demonstrates that the spinal cord is not just a passive conduit for information, but an active processing center capable of making critical, life-saving decisions on its own. It's a beautiful example of how layered and intelligent our nervous system truly is. It's with built-in redundancies and shortcuts to protect us from harm. It's the spinal cord as a guardian, a silent protector, acting before we can even think. But the story doesn't end with simple one-to-one connections. The nerves that branch out from the cord do something remarkable. They don't just travel in straight lines. They weave and braid themselves together into complex networks. Next time, we're going to explore the intricate web of the nerve plexuses. So far, we've pictured the spinal nerves exiting the vertebral column like neat parallel lines, each one heading off to do its own specific job. And while that's a decent starting point, the reality is far more complex, far more robust, and frankly, far more interesting. Nature, it seems, is not a fan of putting all its eggs in one basket. What would happen if a single spinal nerve, say C5, got damaged? Would you lose all function in a specific band of your arm? Potentially, yes. To get around this vulnerability, the nervous system employs a brilliant strategy of redundancy and networking. Shortly after the spinal nerves leave the spinal cord, in most regions of the body, they don't just go their separate ways. Instead, the ventral ramitha branches that head towards the front and sides of the body dive into a complex, interwoven network of other ventral rami from neighboring spinal levels. Think of it like this. Imagine you have 5 separate houses on a street, and each house has its own individual power line going back to the power station. If the line to house number 3 gets cut, house number 3 goes dark. Simple. Now, imagine a different system. The 5 main power lines come from the station, but before they get to the houses, they all feed into a central junction box. In this box, the wires are all mixed and resorted, so that the cable that ends up going to house number 3 contains fibers from the original lines number 2, number 3, and number 4. Now, if the main line number 3 gets cut, house number 3 might experience a brownout, but it won't go completely dark, because it's still receiving power from lines number 2 and number 4. This is the principle of a nerve plexus. It's a system of mixing and redistributing nerve fibers to create new, composite nerves. This means that the major nerves that you find in your limbs, like the radial nerve or the sciatic nerve, are not made up of fibers from just one single spinal level. They are chimeras, composite cables containing contributions from multiple spinal nerves. This provides a huge safety advantage. A minor injury at one spinal root is less likely to cause a complete paralysis of a major muscle or a total loss of sensation in a large area of skin, because those muscles and that skin are likely supplied by fibers from other undamaged spinal roots as well. There are 4 major plexuses in the body. Let's take a quick tour. First, up in the neck, we have the cervical plexus. This is formed from the ventral rami of the first 4 cervical nerves, C1, C4. It's a relatively small plexus, and its nerves primarily supply the skin and muscles of the neck, the head, and the shoulders. But it has one absolute superstar nerve that emerges from it, the phrenic nerve. The phrenic nerve is formed from fibers of C3, C4, and C5, and its sole critical job is to control your diaphragm. The diaphragm is the primary muscle of breathing. This is why the saying C3, 4, 5 keeps the diaphragm alive is drilled into every medical student. A high spinal cord injury, one that damages the cord at or above these levels, can sever the connection to the phrenic nerve, leading to paralysis of the diaphragm and the inability to breathe on one's own. It highlights the profound and immediate importance of these nerve networks. Next, and much larger, is the brachial plexus. This is the big one for the upper limbs. It's located deep in the neck and shoulder. It's a massive, complex network formed by the rami of C5, C6, C7, C8, then T1. The brachial plexus is the grand central station for your entire arm. The fibers from these 5 roots are sorted, mixed, and rebundled through an incredibly complex series of trunks, divisions, and cords, ultimately giving rise to the 5 major nerves of the arm: the musculocutaneous, axillary, median, radial, and ulnar nerves. These 5 nerves are responsible for every single movement and every single sensation you experience in your entire arm, forearm, and hand. Whether you're playing a piano concerto, throwing a baseball, or just feeling the texture of a piece of fabric, you are using the intricate wiring of the brachial plexus. Its complexity is a testament to the incredible dexterity and sensitivity of our hands. Moving down the body, we skip the thoracic region. The thoracic nerves T2, T1, 2 are the exception to the plexus rule. For the most part, they don't form a plexus. They remain separate and travel along the ribs as the intercostal nerves. It's controlling the intercostal muscles for breathing and providing sensation to the chest and abdomen. Then we arrive at the lower back and find the lumbar plexus. Finally, located in the pelvis, we have the sacral plexus. Formed from the rami of L4, L5, S1, S2, S3, and S4, this plexus is all about the posterior. Its nerves supply the buttocks, the perineum, and the posterior thigh, leg, and foot. And emerging from the sacral plexus is the undisputed king of all nerves in the body, the sciatic nerve. The sciatic nerve is the longest and thickest nerve in the entire human body, running from your pelvis all the way down the back of your leg to your foot. It's a massive composite cable containing fibers from 5 different spinal levels, L4, S3. It's responsible for nearly all the muscle control and sensation in the back of your thigh, your lower leg, and your foot. Anyone who has experienced sciatica knows the power of this nerve all too well. So, these plexuses are not just random tangles. They're highly organized, redundant, and efficient distribution hubs. They take the simple, segmented output from the spinal cord and transform it into complex, multifunctional peripheral nerves that are perfectly suited to the complex tasks of moving our limbs and sensing our world. They are another layer of genius in the design of our nervous system, ensuring that it is as resilient as it is capable. Next, we're going to get even more specific. We're going to travel along some of the most important highways within the white matter of the spinal cord itself. The major ascending and descending tracts. We've seen how information gets on and off the spinal cord superhighway via the spinal nerves and their roots. Now, let's take a ride on the highway itself. We're venturing back inside the spinal cord. specifically into the white matter, that vast expanse of myelinated axons that surrounds the gray matter butterfly. As we said before, this white matter is organized into tracts, which are essentially the individual lanes of traffic. You have ascending tracts carrying sensory information northbound to the brain, and descending tracts carrying motor commands southbound from the brain. But these aren't just generic lanes. Each tract is highly specialized, dedicated to carrying a very specific type of information. It's like a highway where one lane is only for sports cars, another is only for refrigerated trucks, and another is only for buses. This high degree of organization is what allows our brain to make sense of the flood of information it receives and to send out precise, targeted commands. Let's start with the northbound traffic, the ascending, sensory tracts. These are our reporters, filing dispatches from the front lines of the body. One of the most important sensory superhighways is a group called the dorsal columns, also known as the posterior columedial lemniscus pathway, but we'll stick with dorsal columns. These tracts are located in the posterior dorsal part of the white matter. Their job is to carry information about fine touch, vibration, and proprioception. Proprioception is your brain's unconscious sense of where your body parts are in space. Close your eyes and touch your nose with your finger. The fact that you can do that without looking is thanks to proprioception, and the dorsal columns are what carry that positional data to your brain. This pathway is all about high-fidelity, detailed information. When you feel the intricate texture of a silk shirt or the subtle vibration of a tuning fork, you're using your dorsal columns. The axons in this tract are fast and heavily myelinated because this is information you need quickly and accurately to interact skillfully with your environment. Now, for a different kind of sensation, we have the spinothalamic tract. This tract is located in the anterolateral part of the white matter. Its job is less about fine detail and more about raw, urgent survival information. The spinothalamic tract carries signals for pain, temperature, and crude touch, like the general feeling of pressure, but not its precise location. When you feel the searing heat from that hot stove or the sharp sting of a needle, that's the spinothalamic tract firing on all cylinders. This is the warning system pathway. It tells your brain about things that could potentially harm you. Interestingly, fibers in this tract cross over to the opposite side of the spinal cord almost immediately after entering, which is a common theme in neuroscience. This is why a spinal cord injury on the right side can cause a loss of pain and temperature sensation on the left side of the body below the injury. There are other ascending tracts too, like the spinocerebellar tracts, which are like a dedicated high-speed data line that goes from your muscles and joints straight to the cerebellum. It's the part of the brain that coordinates movement. This tract doesn't even bother going to the conscious parts of your brain. It's a constant, real-time feed of proprioceptive information that the cerebellum uses to make smooth, coordinated movements. It's the reason you can walk without thinking about every single muscular contraction. Now, let's look at the southbound traffic, the descending motor tracts. These are the messengers carrying orders from the brain's command center. It's the undisputed champion, the main event. The most important motor pathway is the corticospinal tract. This is the pathway for voluntary movement. Conscious, skilled, fine motor control. The very thought that you had to wiggle your pinky finger at the beginning of this journey started in your brain. Cerebral cortex traveled down the massive corticospinal tract, which runs down the lateral part of the white matter, and ended at the motor neuron in your spinal cord that controls your finger. Over 90% of these fibers cross over to the opposite side in the brainstem, which is why your right brain controls your left body, and your left brain controls your right body. This tract is what allows you to write your name, play a guitar, or perform surgery. It's the pathway of intention and precision. Damage to the corticospinal tract is what leads to paralysis, the inability to consciously move your muscles. But not all movement is conscious and precise. Your body is constantly making small, unconscious adjustments to maintain posture and balance. This is handled by a group of other descending tracts, sometimes called the extrapyramidal tracts. For example, the vestibulospinal tract originates from the vestibular nuclei in your brainstem, which are connected to your inner ear's balance organs. This tract sends constant signals down to your postural muscles, helping you stay upright. When you trip on a curb, it stiffs the vestibulospinal tract. It sends lightning-fast commands to your leg and trunk muscles to try and catch your balance before you even have time to think about it. Other tracts, like the reticulospinal and tectospinal tracts, are involved in posture, muscle tone, and reflexive movements of the head and eyes in response to sights and sounds. So, the white matter is not a homogeneous sea of wires. It's a meticulously organized map of dedicated data lines. High-fidelity touch and position data travel up the back and the dorsal columns. Pain and temperature data travel up the side in the spinothalamic tract. Unconscious positional data zips straight to the cerebellum via the spinocerebellar tracts. In coming down, the commands for precise voluntary movements travel in the massive corticospinal tract, while the automatic adjustments for balance and posture are handled by other, more ancient pathways. Understanding this functional geography is key to understanding how the spinal cord works and how it can be affected by injury or disease. Next up, we'll explore another layer of control that is wired through the spinal cord: the autonomic nervous system, the hidden network that runs your body's automatic functions. So far, we've focused almost entirely on the parts of the nervous system you are consciously aware of, the part that lets you feel the world and voluntarily move through it. This is called the somatic nervous system. But all the while we've been talking, a whole other system has been working tirelessly in the background, keeping you alive. Your heart has been beating, your lungs have been breathing, your pupils have been adjusting to the light, your stomach has been digesting your last meal, all without a single conscious thought from you. This is the work of the autonomic nervous system, or ANS. It's the automatic pilot. It's the system that manages all the essential life-sustaining functions of your internal organs. And while it operates largely unconsciously, its command and control pathways are intricately woven into the very structure of the spinal cord we've been exploring. The ANS is famously divided into two main branches, which act like a gas pedal and a brake pedal for your body systems: the sympathetic division and the parasympathetic division. Let's start with the gas pedal, the sympathetic nervous system. This is your fight or flight response. It's designed to prepare your body for intense physical activity, for dealing with threats, stress, and emergencies. When your sympathetic system kicks in, your heart rate skyrockets, your blood pressure increases, your airways open up to take in more oxygen, your pupils dilate to let in more light, and blood is shunted away from non-essential functions like digestion and towards your big skeletal muscles, getting them ready for action. It's a state of high alert, of mobilization. So where does the spinal cord fit into this? The neurons that initiate this whole body-wide alarm bell originate in the spinal cord. Specifically, they are located in the thoracic and upper lumbar regions. But then they do something different. They immediately branch off and enter a chain of ganglia that runs parallel to the spinal cord on both sides. This is called the sympathetic chain, or sympathetic trunk. It looks like a string of pearls running right alongside the vertebral column. Inside these ganglia, the neuron from the spinal cord synapses with a second neuron, which then travels the rest of the way to the target organ, be it the heart, the lungs, or a sweat gland. This to-neuron chain is a classic feature of the ANS. The sympathetic system is designed for a widespread, coordinated response. And this chain allows a signal from the spinal cord to quickly spread up and down the chain, activating multiple organs at once. It's like pulling a single fire alarm that sets off bells on every floor of the building. Now for the brake pedal, the parasympathetic nervous system. This is your rest and digest, or feed and breathe system. It does the opposite of the sympathetic division. It calms the body down, conserves energy, and handles the routine, housekeeping functions. It slows your heart rate, lowers your blood pressure, constricts your pupils, and stimulates digestion and other metabolic processes. It's the state you're in when you're relaxed, reading a book after a good meal. The wiring for the parasympathetic system is quite different. It does not originate from the thoracic and lumbar spinal cord. Instead, its neurons come from two very separate places: the brainstem and the sacral region of the spinal cord, S2, S4. This is why it's sometimes called the craniosacral division. The brainstem component, especially the massive vagus nerve, cranial nerve X, is the real workhorse, handling the parasympathetic control of almost all the organs in your chest and abdomen, the heart, lungs, stomach, intestines. But the sacral part of the spinal cord plays a vital role too. The parasympathetic neurons originating in the gray matter of the S2 to S4 spinal segments send out commands to control the organs of the lower body: the bladder, the rectum, and the reproductive organs. This is why spinal cord injuries in the sacral region can have devastating effects on bladder and bowel control. So, the spinal cord is not just a relay for somatic sensation and movement.
Oh, yes.
It is a critical hub for the autonomic nervous system as well. The entire sympathetic fight or flight system is launched from the thoracic and lumbar regions of the cord. The parasympathetic rest and digest commands for the lower body are launched from the sacral region. This dual system is in a constant state of dynamic balance, a gentle push and pull between the sympathetic and parasympathetic divisions. To keep your internal environment stable or state called homeostasis, the spinal cord is the physical conduit for a huge portion of these vital life-sustaining signals. It's another profound layer of responsibility for our unsung hero, managing not just our interaction with the outside world, but the very functioning of our inner world as well. Next, we are going to create a map of the entire body laid out across the surface of the skin that corresponds directly to the segments of the spinal cord. We're going to explore the fascinating world of dermatomes. We've established that there are 31 pairs of spinal nerves, and each pair exits the spinal column at a specific numbered level C1, T4, L3, and so on. We also know that these nerves carry sensory information from the body back to the spinal cord. Now let's connect those two facts in a way that is both incredibly cool and clinically profound. Each of these spinal nerves is responsible for gathering sensory information from one specific, predictable patch of skin on the body. This patch of skin, innervated by a single spinal nerve, is called a dermatome. The word literally means skin slice. You can think of your entire body, from your neck down to your toes, as being covered in an invisible map, a mosaic of these dermatomes. It's like the whole country is divided into counties, and each county has a dedicated line back to a specific office in the capital. If you look at a dermatome map, it looks a bit strange at first. It's a series of horizontal bands across the torso and long longitudinal strips down the arms and legs. For example, the T4 spinal nerve brings in sensation from the skin at the level of the nipple. The T10 spinal nerve is responsible for the skin around your navel, your belly button. The C6 nerve covers your thumb, C7 your middle finger, and C8 your pinky finger. Down in the legs, the L4 nerve is responsible for the skin over your kneecap, and the S1 nerve wraps around to cover the sole of your foot. This map is a direct result of our embryonic development. As the embryo grows, the segments of the body that will become our skin and muscles are associated with the segments of the developing nervous system. And even as we grow arms and legs that stretch and contort this original segmented plan, that fundamental neurological connection remains. That's why the dermatome map on the limbs looks so stretched and linear. Now, why is this invisible map so incredibly important? For a clinician, a doctor, a neurologist, a physical therapist, the dermatome map is a diagnostic superpower. It's a way to use the patient's own sensory feedback to reverse engineer a problem in the central nervous system. Imagine a patient comes into the emergency room after a car accident and says, "I can't feel anything from my belly button down." The doctor immediately thinks of the T10 dermatome. This suggests that there might be a serious injury to the spinal cord at the T10 level. The signal from the legs and lower abdomen cue and get past that point to ascend to the brain. Or consider someone who comes in complaining of a strange tingling or shooting pain down the outside of their shin and into their big toe. A doctor looking at a dermatome map would recognize this as the territory of the L5 spinal nerve. This points to a problem not necessarily in the leg itself, but potentially further up the chain. The most likely culprit? A herniated disc, one of those shock-absorbing cushions between the vertebrae and the lower back, pressing on the L5 spinal nerve root, right where it exits the spinal column. The problem is in the back, but the symptom is felt far away along the nerve's distribution path. The dermatome map allows the doctor to make that logical leap. By systematically testing sensation in different dermatomes, using a piece of cotton for light touch, a pin for pain, or a cold tuning fork for temperature, a neurologist can precisely map out the boundaries of sensory loss and determine the exact level and extent of a spinal cord lesion or a pinched nerve. It's a non-invasive, powerful diagnostic tool that relies purely on understanding the body's fundamental wiring. There's a related concept for muscles called a myotome. Myotome is the group of muscles that is innervated by a single spinal nerve root. Just like with dermatomes, there's a predictable pattern. For example, the C5 nerve root is primarily responsible for the power to abduct your shoulder, lift your arm out to the side. The L3 nerve root is key for straightening your knee. The S1 root is crucial for pointing your foot downwards, like pressing a gas pedal. So a clinician can test both. He'll test the dermatomes for sensation and the myotomes for muscle strength. If a patient has numbness in the C6 dermatome, the thumb, and also has weakness when they try to bend their elbow, a C6 myotome function. This provides converging evidence that the problem is very likely at the C6 spinal nerve root. It's like getting confirmation from two different sources. This concept also explains a phenomenon called referred pain. Have you ever heard that a classic sign of a heart attack is pain not just in the chest, but radiating down the left arm? Why would a problem with the heart be felt in the arm? It's because the heart's sensory nerves feed back into the spinal cord at the same levels around T1, T5 as the sensory nerves from the arm and chest wall. The brain, which is much more accustomed to receiving pain signals from the arm than from the heart, gets confused by the sudden influx of emergency signals from the heart. It misinterprets the source and refers the pain sensation to the corresponding dermatome, in this case, the inner part of the left arm. It's a case of crossed wires, and it's all because of this shared, segmented wiring plan. The dermatome map is a beautiful illustration of the orderly, segmented, and deeply logical organization of our nervous system. It has a hidden blueprint that reveals the profound connection between the central highway of the spinal cord and every last inch of our body's surface. It allows us to see the invisible and diagnose the hidden, all by understanding the body's own map. We have spent a great deal of time marveling at the spinal cord's incredible design, its robust protection, its complex wiring, and its elegant functionality. But the very importance of this structure also makes it incredibly vulnerable. When the spinal cord is damaged, the consequences can be devastating. Because it is the sole conduit for information between the brain and most of the body, an injury to the cord is like blowing up the one and only bridge off an island. Communication is severed. Spinal cord injury, or SCI, is most often traumatic, caused by a sudden violent blow to the spine from events like car accidents, falls, sports injuries, or acts of violence. This trauma can fracture or dislocate vertebrae, sending bone fragments into the delicate cord, or it can cause the cord to be bruised, stretched, or even torn. The immediate aftermath of a severe injury is a chaotic and destructive process. There's the primary injury, the initial mechanical damage, but then a secondary cascade of events kicks in that can often cause even more damage. Blood vessels can be torn, leading to bleeding and a lack of oxygen in the surrounding nerve tissue. The body's own immune system rushes to the site, and while its intentions are good, the resulting inflammation can cause massive swelling. The spinal cord is housed in that tight, bony vertebral canal, so there's no room for it to swell. This increased pressure can squeeze the cord, further cutting off blood flow and killing even more neurons. It's a vicious cycle of destruction that can spread from the initial injury site. The location of the injury is everything. The level of the injury determines which functions are lost. Because all the nerve tracts have to pass through the point of injury, any damage will affect every single body part that is innervated by the cord below that level. This is why a higher injury is generally more severe. An injury in the cervical region, the neck, is the most devastating. It can lead to quadriplegia, also known as tetraplegia, which is the loss of function in both the arms and the legs. As we discussed with the phrenic nerve, if the injury is at C3, C4, or above, the person will be unable to breathe on their own, because the nerve signals to the diaphragm are cut off. If the injury occurs in the thoracic region, the mid-back, the arms are usually spared, but there will be paralysis and loss of sensation in the legs and trunk. This is called paraplegia. The person will likely need a wheelchair, but they will still have full use of their arms and hands. Injuries in the lumbar or sacral regions of the lower back will also result in paraplegia, but the extent of the paralysis can vary. A lower injury might affect only the feet and ankles, while a higher lumbar injury would affect the entire legs. As we learned when discussing the autonomic nervous system, injuries in the sacral region also critically impact bowel, bladder, and sexual function, as the parasympathetic nerves controlling these organs are located there. The injury can also be complete or incomplete. A complete injury means there is a total loss of all sensory and motor function below the level of the injury. The bridge is completely out. No signals are getting through in either direction. An incomplete injury, on the other hand, means that some signals are still able to get past the damaged area. The bridge is damaged, but maybe one lane is still open. An individual with an incomplete injury might have some movement in one leg, but not the other. They might be able to feel pressure but not pain. The specific symptoms of an incomplete injury depend entirely on which part of the spinal cord, which specific white matter tracts were damaged, and which were spared. For example, if the back part of the cord is damaged, a person might lose their sense of fine touch and proprioception from the dorsal columns, but still be able to feel pain and temperature from the spinothalamic tract, and still be able to move their muscles from the corticospinal tract. This is known as posterior cord syndrome. Conversely, an injury to the front of the cord might wipe out motor function and pain, temperature sensation, but leave fine touch intact. The patterns of these deficits are like neurological fingerprints that can tell a doctor exactly where the damage is. Living with a spinal cord injury is a life-altering challenge that goes far beyond just the inability to move. There are chronic pain issues, problems with regulating blood pressure and body temperature, increased risk of infections, and profound psychological and social hurdles. It requires a complete relearning of how to live and interact with the world. For a long time, the central dogma was that the central nervous system, the brain, and spinal cord could not heal. Once a neuron was dead, it was gone forever. But our understanding is beginning to change. The field of neuroscience is buzzing with research into spinal cord injury, exploring everything from advanced surgical techniques and sophisticated drug therapies to reduce secondary damage, to revolutionary ideas like stem cell transplantation to replace dead neurons, nerve grafts to bridge the gap in electrical stimulation of the spinal cord below, the injury to reawaken dormant neural circuits. While a true cure for paralysis remains the holy grail, the progress is real. We are beginning to understand the immense complexity of the spinal cord, not just in its healthy state, but in its injured state as well. The study of what goes wrong teaches us an incredible amount about how it all works so perfectly right in the first place. But trauma isn't the only way things can go wrong. Next time, we'll look at diseases and conditions that can affect the spinal cord and nerves from the inside out. Traumatic injury is a sudden, violent assault on the spinal cord from the outside. But the spinal cord and its nerves can also be attacked from within by a host of diseases and degenerative conditions. These processes can be just as devastating, often progressing slowly and insidiously, gradually eroding the functions we take for granted. Let us explore a few of these conditions to understand how they disrupt the delicate machinery we've been studying. One of the most well-known diseases of the central nervous system is multiple sclerosis, or MS. Remember our discussion of the white matter and the critical importance of the myelin sheath, the fatty insulation that allows nerve signals to travel quickly and efficiently? MS is fundamentally a disease of myelin, for reasons we still don't fully understand. The body's own immune system mistakenly attacks and destroys the myelin in the brain and spinal cord. When the myelin is destroyed, it leaves behind scarred areas, or plexus is the sclerosis. It's like the rubber insulation has been stripped off a wire, leaving the bare copper exposed. When this happens, the transmission of the nerve signal is severely disrupted. It might be slowed down, distorted, or stopped altogether. Because these demyelination lesions can occur randomly anywhere in the white matter of the brain or spinal cord. The symptoms of MS are incredibly varied and unpredictable. If a lesion forms on the dorsal columns in the spinal cord, a person might experience numbness or a tingling pins and needles sensation. If it forms on the corticospinal tract, they might experience muscle weakness, stiffness, or spasms. If the lesion is on the spinocerebellar tract, it could lead to problems with balance and coordination. The disease often follows a relapsing-remitting pattern, where a person has flare-ups of symptoms followed by periods of recovery. But the damage can accumulate over time, leading to progressive disability. MS is a direct and devastating illustration of why the white matter and its myelin is not just filler tissue, but a critical component for high-speed communication. Now let's look at another, equally cruel neurodegenerative disease, amyotrophic lateral sclerosis, or ALS, also known as Lou Gehrig's disease. If MS is a disease of the insulation myelin, ALS is a disease of the wires themselves. Specifically, ALS targets and kills motor neurons. It attacks both the upper motor neurons, the ones that make up the descending tracts like the corticospinal tract, with their cell bodies in the brain, and the lower motor neurons, the ones whose cell bodies are in the ventral horn of the spinal cord's gray matter and whose axons go out to the muscles. As these motor neurons die, the brain's ability to initiate and control voluntary movement is progressively lost. It often starts subtly, perhaps as weakness in a hand or a foot or slurred speech, but it inexorably spreads. The muscles, no longer receiving signals from the nerves, begin to atrophy and waste away. The amyotrophic part of the name literally means no muscle nourishment. Over time, people with ALS lose the ability to walk, to speak, to swallow, and eventually to breathe, as the motor neurons controlling the diaphragm cease to function. The truly tragic part of ALS is that it typically does not affect a person's senses or their cognitive abilities. The sensory pathways, the dorsal columns, the spinothalamic tract are left completely intact. The mind remains sharp and aware, but becomes progressively trapped inside a body it can no longer command. It is the ultimate heartbreaking disconnection between brain and body, caused by the death of the very neurons in the ventral horn and corticospinal tracts that we have identified as the essential off-ramps and southbound lanes of the motor system. There are also diseases that specifically target the peripheral nerves after they've left the spinal cord. One dramatic example is Guillain-Barré syndrome. Much like MS, this is an autoimmune condition, but instead of attacking the myelin in the central nervous system, it attacks the myelin of the peripheral nerves. It often comes on very suddenly, frequently after a minor viral or bacterial infection. It typically starts with a tingling and weakness in the feet and legs that rapidly spreads upwards over days or weeks. In severe cases, it can lead to almost total paralysis, including the muscles for breathing, requiring mechanical ventilation. It's a terrifying condition because of its speed, but unlike MS or ALS, most people with Guillain-Barré syndrome eventually recover, as the peripheral nervous system has a much greater capacity for myelin repair than the central nervous system. These diseases, in their own unique and terrible ways, are experiments of nature. They selectively dismantle parts of the nervous system, and by observing the consequences, we gain a deeper and more profound appreciation for the function of each individual component: the myelin sheath, the motor neurons in the gray matter, the descending tracts, and for the beautiful, intricate, and fragile system they form together. We've spent a lot of time focusing on the spinal cord itself, the great central highway. But that highway is only as good as the local roads it connects to. The peripheral nerves, the 31 pairs of on-ramps and off-ramps that spread throughout our body, are themselves susceptible to a wide range of problems that can disrupt the flow of information. Damage or disease affecting these nerves is broadly known as peripheral neuropathy, unlike the well-protected spinal cord, encased in bone and floating in fluid. The peripheral nerves are much more exposed as they travel through our limbs. They have to pass through tight tunnels, around bony corners, and through tissues that are constantly moving and stretching. This makes them vulnerable to physical compression and damage. Think about carpal tunnel syndrome. This is a classic example of a peripheral neuropathy caused by compression. The median nerve, one of the major nerves of the arm that arises from the brachial plexus, has to pass through a narrow passageway in the wrist called the carpal tunnel, along with a number of tendons. If those tendons become inflamed and swollen, usually from repetitive motions, they can squeeze the median nerve. The result? Pain, numbness, and tingling in the hand, specifically in the thumb index. In middle fingers, the exact area of skin the median nerve is responsible for. It's a traffic jam on a local road. It's preventing sensory information from getting through properly and causing faulty signals, the tingling, to be generated. Another common example is sciatica, which we touched on before. This isn't a condition in itself, but a symptom. It refers to pain that radiates along the path of the sciatic nerve. The most common cause, as we mentioned, is a herniated disc in the lumbar spine pressing on one of the nerve roots, L4, L5, S1, S2, or S3, that form the sciatic nerve. The problem is at the on-ramp, but the pain is felt all the way down the highway and its exit ramps in the leg. The immense size of the sciatic nerve is why this condition can be so debilitating, affecting the entire back of the leg. But neuropathy isn't just about physical pinching. It can also be caused by systemic, body-wide diseases. By far the most common cause of peripheral neuropathy worldwide is diabetes. Over time, high levels of blood sugar are toxic to nerves and to the tiny blood vessels that supply them with oxygen and nutrients. This damage, known as diabetic neuropathy, usually starts in the longest nerves, first the ones that have to travel all the way to the feet. This is why people with diabetes often first experience a stalking love pattern of symptoms. It begins with numbness, tingling, or burning pain in the toes and feet, the stocking area, and can gradually progress up the legs. Later, the same symptoms may appear in the fingers and hands, the glove area. This loss of sensation is incredibly dangerous. A person might not feel a small cut, a blister, or a burn on their foot. That minor injury can then become infected and, without the warning signal of pain, can lead to severe ulcers and, in the worst cases, amputation. It's a tragic example of what happens when the body's sensory alarm system is silenced. Diabetic neuropathy can also affect the autonomic nerves, leading to problems with digestion, blood pressure regulation, and other internal functions. Toxins and nutritional deficiencies can also wreak havoc on peripheral nerves. Chronic alcoholism can lead to a neuropathy, partly because of the direct toxic effect of alcohol, and partly because it often leads to deficiencies in essential B vitamins, like thiamine, which are crucial for nerve health. Certain chemotherapy drugs, while effective at killing cancer cells, can also damage healthy nerve cells, causing a painful condition called chemotherapy-induced peripheral neuropathy. So while the spinal cord is the command center, the peripheral nervous system is the vast network of field agents. And these agents are vulnerable. Whether it's a physical pinch in a narrow tunnel, a toxic environment created by high blood sugar, or an autoimmune attack. Damage to these peripheral lines can cut off entire regions of the body from the central nervous system, leading to a loss of sensation, a loss of movement, and the presence of debilitating pain. It underscores the fact that the entire system, from the brain to the tip of the smallest nerve in your toe, is a single, interconnected, and fragile entity. There's a fascinating and slightly strange anatomical fact that we haven't discussed yet. If you were to look at a full-grown adult, you'd find that the spinal cord itself does not run the entire length of the vertebral column. Your backbone goes all the way down to your tailbone or coccyx, but the spinal cord, the actual bundle of nervous tissue, stops much higher up. In most adults, the spinal cord proper ends around the level of the first or second lumbar vertebra, L1 or L2, in the lower back. Why is this? It's a result of a developmental race. In a very young fetus, the spinal cord and the vertebral column are the same length. But as the fetus grows, the bones of the vertebral column grow much faster and longer than the nervous tissue of the spinal cord. The spinal cord is essentially left behind. Its top end is fixed to the brain, so as the bony column elongates beneath it, the cord's bottom end gets pulled upwards relative to the vertebrae. So, what fills that empty space in the vertebral canal below L2? The spinal cord may end, but the spinal nerves still need to exit the vertebral column at their designated levels. The lumbar, sacral, and coccygeal nerves still have to get out at the L3, L4, L5, S1, and so on. Intervertebral foramina. The solution is elegant. As the spinal cord ends, the nerve roots for all the lower levels of the body have to travel downwards from the end of the cord, through the vertebral canal until they reach their correct exit point. This results in a remarkable structure. The very tip of the spinal cord is a cone-shaped ending called the conus medullaris, and cascading downwards from this cone is a bundle of individual spinal nerve roots floating in the cerebrospinal fluid. This spray of nerve roots is known as the cauda equina, which is Latin for horse's tail, because that's exactly what it looks like to early anatomists. So, the lower part of your vertebral canal from about L to downwards doesn't contain the solid spinal cord. Instead, it contains this loose collection of nerve fibers, the cauda equina, bathing in the CSF-filled subarachnoid space. This unique anatomy has profound clinical implications. First, it creates a much safer place for doctors to perform certain procedures. Imagine needing to take a sample of that cerebrospinal fluid to test for meningitis or multiple sclerosis. You would not want to stick a needle into the solid spinal cord. The risk of damaging critical nerve tracts would be enormous. But in the lower lumbar region, you can insert a needle into the subarachnoid space and be reasonably sure you and hit the solid cord, 'cause it isn't there. You'll be entering the space filled with the cauda equina. The nerve roots are floating relatively freely in the fluid, and a fine needle will usually just push them aside without causing any damage. This procedure is a lumbar puncture or a spinal tap, and it's done safely thousands of times a day precisely because of this anatomical arrangement. The cauda equina is also where epidural anesthesia is often administered, for example, during childbirth. The goal of an epidural is to bathe the nerve roots in anesthetic medication to block pain signals coming from the lower body. The needle is inserted into the epidural space, the space just outside the dura mater, the lower lumbar region, allowing the anesthetic to numb the very nerve roots of the cauda equina that are responsible for transmitting the pain of labor. However, the cauda equina itself can be damaged. A massive herniated disc, a tumor, or a severe fracture in the lower lumbar region can compress this whole bundle of nerves. This is a neurosurgical emergency called cauda equina syndrome. The symptoms are dramatic: severe low back pain, paralysis, or weakness in the legs, as both motor and sensory roots are affected, and, critically, a loss of bowel and bladder control due to the compression of the sacral parasympathetic nerves. It requires immediate surgery to relieve the pressure, because if left for too long, the damage to these nerve roots can become permanent. Anchoring this whole structure at the very bottom is one final delicate thread, a thin filament of connective tissue, an extension of the pia mater. Continues down from the tip of the conus medullaris all the way to the coccyx, where it anchors the spinal cord in place. This is the filum terminale, the terminal thread. So, this lower end of the spinal canal is a region of unique and critical anatomy. The cone-shaped end of the cord conus medullaris, the leash-like anchor filum terminale, and the great dangling spray of nerve roots that gives the region its equine name, cauda equina. It's a beautiful solution to a developmental puzzle and a region of immense clinical importance. We've talked a lot about the anatomy of the spinal cord and nerves from a theoretical perspective. But let's take a moment to look at it from a practical clinical standpoint. How do doctors interact with these structures to diagnose and treat patients? We've already touched upon a couple of procedures, but let's dive a little deeper into the incredible precision required to navigate this delicate territory. Let's revisit the lumbar puncture, or spinal tap. The anatomy we just discussed, the cauda equinis, what makes it possible. Procedure is a marvel of applied anatomy. A patient is usually asked to lie on their side and curl up, or sit and lean forward. The goal is to arch the lower back, which opens up the spaces between the spinous processes of the lumbar vertebrae, making it easier to insert the needle. The doctor will feel for the patient's hip bones, the iliac crests, and a line drawn between them usually crosses the spine at the L4 level. This gives them a landmark. They will aim for the space just above or below this, typically the L3, L4, or L4, L5 space, knowing they are well below the end of the solid spinal cord. Then, the needle is inserted with incredible care. The doctor can actually feel the different layers as the needle passes through them. First the skin, then the subcutaneous fat, then the tough supraspinous and interspinous ligaments. There is a distinct pop that is often felt as the needle pierces the ligamentum flavum, and then another, as it punctures the tough dura mater and the arachnoid mater. Once the needle is in the subarachnoid space, the cerebrospinal fluid, which is normally crystal clear like water, will begin to drip out. This fluid can then be collected and sent to the lab to be analyzed for signs of infection, like bacteria or white blood cells in meningitis, inflammation like specific proteins in MS, or bleeding. The pressure of the CSF can also be measured, which can be important for diagnosing certain conditions. It is a direct window into the chemical environment of the central nervous system. Now, let's contrast that with an epidural. The name tells you exactly where you're going. Epi means upon or outside of. So, an epidural is an injection into the space outside the dura mater. This is the epidural space. It's not an empty space. It's filled with fat, connective tissue, and a network of blood vessels. For an epidural anesthetic, The goal is to get close to the spinal nerves as they exit the dura, but not to puncture the dura itself. The needle is advanced through the same initial layers, but the doctor stops just after the pop of the ligamentum flavum before reaching the dura. A catheter can then be threaded into this space, and anesthetic medication can be dripped in continuously to provide prolonged pain relief. The medication soaks through the tissues and numbs the nerve roots in that region. This same space can be used for steroid injections to treat chronic back pain. If a patient has an inflamed herniated disc that is irritating a nerve root, injecting a powerful anti-inflammatory steroid directly into the epidural space at that level can calm the inflammation and provide significant pain relief, allowing the body time to heal. Moving beyond needles, modern imaging has revolutionized how we view the spinal cord. Magnetic resonance imaging, or MRI, is the gold standard. Unlike an X-ray, which is great for looking at bones, an MRI provides exquisitely detailed images of soft tissues. A spinal MRI can clearly show the spinal cord itself, the intervertebral discs, the spinal nerves, and the surrounding ligaments. Doctors can use an MRI to see a herniated disc physically pressing on a nerve root. They can see the inflammatory plaques of multiple sclerosis in the white matter of the cord. They can visualize tumors, infections, or swelling from an injury. The ability to see this anatomy non-invasively has transformed the diagnosis of spinal disorders. And in the operating room, neurosurgeons perform miracles of microsurgery on these structures. Using high-powered microscopes and incredibly fine instruments, they can remove bone spurs or pieces of a herniated disc that are compressing a nerve. A procedure called a discectomy or a laminectomy. They can remove tumors from within the spinal cord itself, painstakingly separating the tumor from the critical nerve tracts surrounding it. They can stabilize a fractured spine with rods and screws, protecting the cord from further damage. From the simple diagnostic tap of a reflex hammer to the high-tech precision of an MRI scanner and the delicate skill of a neurosurgeon's hand. Modern medicine is a testament to our profound and ever-growing understanding of the spinal cord's intricate anatomy. Every procedure is a conversation with the body's wiring, a dialogue based on a detailed map that allows us to diagnose, to heal, and to protect this most vital of structures. Like any tissue in the body, the spinal cord is a living, metabolically active structure. Its neurons are constantly firing, maintaining electrical gradients, and communicating with each other, a process that consumes a tremendous amount of energy, and that energy has to come from somewhere. The spinal cord requires a constant, uninterrupted supply of oxygen and glucose, delivered by a dedicated and highly specialized network of blood vessels. Cut off this supply for even a few minutes, and the nerve cells will begin to die, leading to irreversible damage. The blood supply to the spinal cord is both elegant and precarious. It's primarily fed by three main arteries that run vertically along its length like fuel lines running down a rocket. There is one single large anterior spinal artery. This artery runs right down the front of the spinal cord, nestled in a groove called the anterior median fissure. It's the big workhorse, supplying blood to the anterior two-thirds of the spinal cord. This is a huge and critically important territory. It includes the ventral horns of the gray matter where the motor neurons live, the lateral horns for the autonomic nervous system, and the massive white matter tracts like the corticospinal and spinothalamic tracts. Essentially, the anterior spinal artery is responsible for powering almost all of your motor function and your pain and temperature sensation. Then there are two smaller posterior spinal arteries. These run down the back of the cord, one on the left and one on the right. They are responsible for supplying blood to the posterior one-third of the cord. Their main job is to feed the dorsal columns those high-fidelity tracts that carry information about fine touch, vibration, and proprioception. Now you might be thinking, 3 small arteries to supply the entire length of the spinal cord? That doesn't seem very robust, and you'd be right. These 3 longitudinal arteries are not sufficient on their own. They need to be fed and reinforced along their entire length. This is where a supporting cast of vessels comes in. At various levels, segmental arteries branch off from the aorta, the body's main artery, and other major vessels. As they approach the vertebral column, they give off branches called radicular arteries that enter the intervertebral foramen alongside the spinal nerves. Most of these just supply the nerve roots themselves, but a few of them are much larger, and continue on to connect with and feed into the anterior and posterior spinal arteries. These are the crucial feeder arteries that bolster the main supply. There is one particularly large and important feeder artery, usually located in the lower thoracic or upper lumbar region, called the artery of Adamkiewicz. This is the dominant feeder artery for the lower two-thirds of the spinal cord. Its location can vary from person to person, which is a major concern for surgeons operating on the aorta in that region. If this artery is accidentally clamped or damaged during surgery, it can starve the lower spinal cord of blood, resulting in paralysis of the legs. This whole system creates what are known as watershed areas. These are regions of the spinal cord that are at the very end of the supply line from two different feeder arteries. The mid-thoracic region around T4-T8 is a notorious watershed area. The blood supply here is less robust than in the cervical or lumbar regions. This makes this part of the cord particularly vulnerable to ischemia, lack of blood flow. If a person's blood pressure drops dangerously low for a prolonged period, for example during a cardiac arrest or major trauma, this vulnerable mid-thoracic region is often the first part of the spinal cord to suffer damage simply because it has the most tenuous blood supply. When the blood supply to the cord is compromised, it results in a spinal cord stroke or spinal cord infarction. It's much rarer than a stroke in the brain, but the effects are just as devastating. The symptoms will depend entirely on which artery is blocked. If the single anterior spinal artery is blocked, it leads to anterior cord syndrome. A person will suddenly lose all motor function and all pain and temperature sensation below the level of the blockage. However, because the posterior spinal arteries are still working, their fine touch, vibration, and proprioception in the dorsal columns will be completely preserved. It is a bizarre and specific set of deficits that points directly to a problem with that one major blood vessel. The vascular network of the spinal cord is a masterpiece of biological engineering, but it's a system with inherent vulnerabilities. Its reliance on a few key longitudinal arteries, bolstered by a variable number of feeder arteries, means that it lives on a knife's edge. It's a powerful reminder that every electrical signal, every sensation, every movement, is ultimately powered by the simple, life-giving flow of blood. How does this impossibly complex structure, this fortress of bone, this butterfly of gray matter, and this meticulously organized highway of white matter come to be? The story of the spinal cord begins in the earliest moments of embryonic development, and it is a story of folding, signaling, and migration that is one of the true wonders of biology. Just a couple of weeks after conception, the developing embryo is a simple three-layered disc. The top layer is called the ectoderm, and it is from this layer that our entire nervous system and our skin will arise. A chemical signal from the layer below it causes a section of the ectoderm running down the midline of the embryo to thicken. This thickened strip is called the neural plate. This is the very first whisper of a nervous system. What happens next is a beautiful piece of biological origami. The edges of this neural plate begin to rise up, forming neural folds. The center of the plate begins to dip down, creating a neural groove. These folds continue to grow upwards and towards each other, like you're folding a piece of paper in half lengthwise. Eventually, the tips of the folds meet in the middle and fuse together, creating a hollow, closed structure, the neural tube. This fusion starts in the middle of the embryo, what will become the cervical region, and zips up towards the head and down towards the tail. This entire process is called neurulation, and it is the birth of our central nervous system. The hollow tube will eventually develop into the brain at the top end and the spinal cord at the bottom end. The hollow space inside will remain, becoming the ventricles of the brain and the tiny central canal that runs down the middle of the spinal cord. As these neural folds were coming together to fuse, a special group of cells at the very crest of the folds were pinched off and came to lie just outside the newly formed neural tube. These are the neural crest cells, and they are some of the most remarkable and versatile cells in the entire body. They are master travelers. They detach and migrate all over the developing embryo, giving rise to an astonishing variety of different tissues. In the context of our story, they are absolutely crucial. Neural crest cells will develop into, among many other things, the neurons of the dorsal root ganglia, those Olympian cell bodies of our sensory neurons. They also form the ganglia of the autonomic nervous system and the Schwann cells that produce the myelin for the peripheral nerves. Meanwhile, Back at the neural tube, the cells that will form the spinal cord begin to differentiate and organize themselves. The tube develops a distinct top and bottom, or rather a back and a front. The dorsal back part of the tube, under the influence of one set of chemical signals, develops into the alar plate. The cells of the alar plate will become the inner neurons of the dorsal horn, the receiving station for sensory information. The ventral front part of the tube, under the influence of a different set of signals, develops into the basal plate. The cells of the basal plate will become the motor neurons of the ventral horn, the command center for movement. This early division into a sensory back half and a motor front half is the developmental origin of the strict one-way traffic system of the dorsal and ventral roots. It's a fundamental organizing principle that is laid down before the first neuron has even fired. As the spinal cord grows, motor axons begin to sprout from the basal plate and grow outwards to find and connect with their target muscles. At the same time, the developing sensory neurons from the neural crest-derived dorsal root ganglia send their axons in two directions. One branch grows out to the skin and periphery, and the other grows into the dorsal side of the neural tube, establishing the sensory connections. Sometimes, this intricate process of folding and fusion can go wrong. If the neural tube fails to close properly at the bottom end, it can result in a birth defect known as spina bifida. In its most severe form, parts of the spinal cord and meninges can be left exposed on the baby's back, leading to paralysis and other neurological problems. The importance of this closure process is why folic acid is so strongly recommended for women who are planning to become pregnant. This simple B vitamin plays a critical role in the chemical reactions required for successful neural tube closure. From a simple flat sheet of cells to a complex, multi-layered, perfectly wired tube, the development of the spinal cord is a breathtaking cascade of precisely timed events. It is a blueprint written in the language of genes and chemical gradients, a dance of cellular migration and differentiation that builds, from scratch, the information superhighway that will last a lifetime. For over a century, the prevailing dogma in neuroscience, famously articulated by the great Spanish neuroanatomist Santiago y Cayel, was that the adult central nervous system was fixed and immutable. Nerve pathways were established in development, and after that, the circuits were set. If you damaged them, they were gone for good. There was no regeneration, no repair. This belief contributed to a sense of hopelessness surrounding conditions like spinal cord injury. However, in recent decades, this dogma has been shattered. We now know that the nervous system, including the spinal cord, possesses a remarkable, albeit limited capacity for change and reorganization. This ability is called neuroplasticity. The spinal cord doesn't have the dramatic plasticity of the brain. And while it certainly can't regrow itself after being severed, there are subtle but important adaptive processes at play. One of the key challenges to regeneration in the central nervous system is the environment. After an injury, the area becomes a hostile place for a neuron to regrow. Glial cells, which are normally the supportive staff, form a dense glial scar around the injury site, which acts as a physical and chemical barrier to any axons trying to grow across it. Furthermore, the very myelin in the CNS, produced by cells called oligodendrocytes, contains chemical signals that actively inhibit axon growth. This is in stark contrast to the peripheral nervous system, where the Schwann cells that produce myelin actually release growth-promoting factors, which is why peripheral nerves can regenerate, albeit slowly and imperfectly. It seems the CNS has evolved to prioritize stability over regeneration, perhaps to prevent faulty connections from forming in its incredibly complex circuits. But even in the face of these obstacles, the spinal cord can adapt. Following an incomplete injury, where some pathways are spared, neuroplasticity is the key to recovery. The remaining intact neural circuits can reorganize themselves to try and compensate for the ones that were lost. This can happen in several ways. One way is through axonal sprouting. Healthy, undamaged axons that run near the injured area can sprout new little branches, like a tree growing a new limb. These new sprouts can travel a short distance to form new connections, or synapses, with neurons that have lost their original input. It's like a neighbor running an extension cord over to your house after your power line has been cut. This can help to reestablish some degree of communication and function in the circuits below the injury. Another form of plasticity involves the strengthening of existing weaker pathways. There are many redundant and less used pathways in the spinal cord. After the main highway, like the corticospinal tract, is damaged, these minor side roads can, with training, be strengthened and take on a greater role in transmitting signals. The nervous system essentially learns to reroute traffic around the accident. This is the entire basis for modern neurorehabilitation. Physical and occupational therapy after a spinal cord injury are not just about strengthening muscles. They are about driving neuroplasticity, repetitive, task-specific training, like repeatedly practicing standing, walking on a treadmill with body weight support, or gripping an object bombards the spinal cord with sensory feedback and motor commands. This intense activity encourages the surviving neural circuits to reorganize, sprout new connections, and optimize their function. The goal is to teach the spinal cord how to work with what it has left. Scientists are now exploring ways to supercharge this natural plasticity. Electrical stimulation of the spinal cord below the level of injury, through implanted devices, has shown incredible promise. This epidural stimulation doesn't generate movement on its own, but it seems to wake up the dormant spinal circuits, raising their overall level of excitability. This makes them more responsive to the weak, residual signals that might still be trickling down from the brain. When this stimulation is combined with intense physical therapy, some patients who are completely paralyzed have been able to regain voluntary movement, stand, and even take steps. It's a stunning demonstration of the latent potential locked within the spinal cord's own circuitry. So while the spinal cord is not the regenerative powerhouse we wish it was, it is not a static, hardwired cable. It is a dynamic, adaptable system that is constantly remodeling its connections in response to experience. Understanding and harnessing this innate plasticity is the most exciting frontier in the treatment of spinal cord injury, offering a tangible path from a dogma of permanence to a new science of recovery. Let's make this personal. Let's trace the complete journey of a single simple sensation. Right now, reach into your pocket and feel for a key. Pay attention to the feeling. The cold, hard metal, the sharp serrated edge, the smooth, worn surface of the bow. You consciously perceive all of that in a fraction of a second. But the neural journey that information took is an epic voyage through the nervous system. It all begins at the receptor. Embedded in the skin of your fingertips are a variety of highly specialized sensory receptors. For the fine details of the key's shape and texture, the stars of the show are Meissner's corpuscles and Merkel's discs. These are machinorestors, meaning they respond to physical deformation. As you run your finger over the key's teeth, you are physically pressing on these tiny receptors, causing them to fire off a volley of electrical signals action potentials. The pattern of this firing encodes the information: a high-frequency burst for a sharp edge, a slower, more sustained firing for steady pressure. This electrical message now begins its ascent, traveling along the axon of a primary sensory neuron. This neuron's axon is part of a peripheral nerve in your arm, perhaps the median nerve. It travels up your forearm, through your elbow, up your arm, and through the brachial plexus in your shoulder. Its cell body, the neuron's little life support center, is sitting just outside the spinal cord in the dorsal root ganglion, at, say, the C7 level. The signal zips past the cell body without stopping and continues along the central part of the axon, heading for the on-ramp to the spinal cord. The axon enters the spinal cord through the dorsal root of the C7 spinal nerve. If this were a pain signal, it would enter the gray matter and immediately cross over. But this is not pain. This is high-fidelity information about fine touch and texture. It immediately turns upwards and enters the fast lane, the dorsal columns, specifically a part called the fasciculus cuneatus, which carries information from the upper body. Our signal now rockets up the spinal cord, staying on the same side it entered. It travels the entire length of the cord through the thoracic region, up through the rest of the cervical region, and enters the brainstem. Its first stop, its first synapse, is in a region of the lower medulla called the nucleus cuneatus. Here, our primary sensory neuron finally ends, passing its message on to a secondary neuron. The journey is far from over. The axon of this secondary neuron now does something crucial. It crosses over to the opposite side of the brainstem, in a great sweep of fibers called the medial lemniscus. This is the great decassation, the crossover point. This is why the left side of your brain perceives sensations from the right side of your body. Now on the opposite side, the signal continues its ascent through the rest of the brainstem, and arrives at the next major relay station for almost all sensory information, the thalamus. Deep in the center of the brain, the thalamus acts as a grand sorting office and switchboard. Our signal arrives, synapses with a third neuron in the chain, and gets routed to its final destination. The axon of this third neuron leaves the thalamus and travels to a specific strip of the brain's outer layer, the cerebral cortex located in the parietal lobe. This area is called the primary somatosensory cortex. And it's here, and only here, that the electrical signals that began in your fingertip are finally interpreted as the conscious perception of cold, hard, sharp key. What's more, the signal arrives at a very specific point on a map of the body laid out across this cortex. There's a region for the fingers right next to a region for the hand, next to one for the arm, and so on. The brain knows the signal came from your finger because it arrived at the finger part of the map. So let us recap that incredible voyage. Receptor in the fingertip, greater than peripheral nerve. Dorsal root, ganglion greater than dorsal columns of the spinal cord. Same side, greater than medulla synapse, and crossover greater than thalamus synapse. Greater than primary somatosensory. Cortex conscious perception. It is a 3-neuron chain, a high-speed, high-fidelity data transfer that crosses continents of your own body, crosses over to the other side of your world, and delivers its message with pinpoint accuracy. Every time you touch something, you are initiating this remarkable transcontinental relay race. It all depends on the integrity of that first long leg of the journey, up the pristine white matter tracts of the spinal cord. Now, let's reverse the journey. The sensation of the key in your pocket has been processed. You've identified it. You make the conscious decision. I'm going to take the key out of my pocket. That simple intention is the start of another incredible journey, this time traveling in the opposite direction from the brain down to the muscles of your hand. This is the story of a motor command. The decision to move originates in the highest levels of your brain, in the frontal lobes. The plan is formulated, the sequence of movements is determined, the final go. Order is given by a specific strip of cortex in the frontal lobe, just in front of the sensory cortex we just visited. This is the primary motor cortex. Just like the sensory cortex, this area also has a map of the body, a motor homunculus. The command to move your fingers originates from the finger area of this map. The neurons in the primary motor cortex that initiate this command are the upper motor neurons. These are the giants of the nervous system with some of the longest axons in the body. A single upper motor neuron can have its cell body in your brain and its axon terminal all the way down in your lumbar spinal cord. So, the command begins as an electrical signal in the cell body of an upper motor neuron in your cerebral cortex. The axon of this neuron plunges down from the cortex, deep into the brain. It joins with hundreds of thousands of other motor axons to form a massive, tightly packed bundle of fibers. This is our southbound superhighway, the corticospinal tract. This tract travels down through the brain, passing through structures like the internal capsule and the midbrain. It then enters the brainstem. In the lower part of the brainstem, the medulla. The corticospinal tract forms two prominent bumps on the front surface called the medullary pyramids. And it's here, in the pyramids, that the most famous crossover in the nervous system occurs. About 90% of the fibers in the corticospinal tract cross over to the opposite side. This is the decussation of the pyramids. This is why your left motor cortex controls the right side of your body. Our command, which started in the left brain to move our right hand, is now on the right side of the central nervous system. After crossing over, the tract, now called the lateral corticospinal tract, continues its journey down into the spinal cord. It travels in the lateral part of the white matter, descending level by level, passes through the thoracic cord, and finally arrives at the cervical enlargement, the area of the cord that controls the arms and hands. At the C7 or C8 level, our specific upper motor neuron axon finally reaches its destination within the spinal cord. It leaves the white matter highway and enters the gray matter butterfly. It heads for the ventral horn, the shipping department. Here, our upper motor neuron from the brain will finally talk to the next neuron in the chain, the lower motor neuron. The synapse between the upper and lower motor neuron is a critical control point. The upper motor neuron releases a neurotransmitter, telling the lower motor neuron to fire. The lower motor neuron is the final common pathway, is the last link in the chain of command. Its cell body sits in the ventral horn. Once it receives the go signal, it generates its own action potential. Its axon then leaves the spinal cord through the ventral root, the motor off-ramp. It joins the C8 spinal nerve, travels through the brachial plexus, down the arm in one of the peripheral nerves, perhaps the ulnar or median nerve. The axon travels all the way down to a specific muscle in your forearm or hand, one of the muscles responsible for flexing your fingers. The axon then branches out and connects to several muscle fibers at a specialized synapse called the neuromuscular junction. Here, the nerve releases a chemical called acetylcholine, which triggers the muscle fibers to contract. The coordinated contraction of several of these muscles flexes your fingers, curls them around the key, while other commands are simultaneously sent to contract your biceps and deltoid to lift your arm. Pulling the key from your pocket, let us recap this command and control mission. Primary motor cortex intention greater than corticospinal tract. Descends through brain greater than medullary pyramids crossover, greater than lateral corticospinal tract, descends through spinal cord, greater than ventral horn of gray matter, synapse greater than lower motor neuron, greater than ventral root, greater than peripheral nerve, greater than neuromuscular junction, muscle contraction action. From a simple thought to a physical action, the signal has traveled from the highest office in the brain, down the express elevator of the corticospinal tract, crossed the border in the brainstem, and handed off its orders to a local agent in the spinal cord, who then delivered the message directly to the workers on the factory floor. It is a chain of command of breathtaking speed and precision, and the spinal cord is its essential, irreplaceable conduit. We've been talking about spinal nerves and peripheral nerves as if they are single entities, simple wires running from the spinal cord to the body. But if you were to look at a peripheral nerve, like the sciatic nerve or the ulnar nerve, under a microscope, you would find that it's not a single wire at all. It's a massive, complex, and beautifully structured communications cable, containing thousands of individual wires, all bundled and protected in a highly organized fashion. The internal structure of a peripheral nerve is a testament to nature's brilliant engineering. Let's start with the smallest unit, a single axon. This is the long, slender projection of a single neuron. It might be a motor axon carrying a command to a muscle, or a sensory axon carrying information from the skin. Each individual axon, especially the larger ones, is wrapped in its own myelin sheath, the fatty insulation we've talked so much about, which is produced by Schwann cells in the periphery. But the protection doesn't stop there. Each individual myelinated axon is then surrounded by a delicate, paper-thin layer of connective tissue. This is the endoneurium. The endoneurium is like the thin plastic coating on a single copper wire inside a larger electrical cable. It provides electrical insulation and helps create the right chemical environment for the axon. Now, neurons don't like to travel alone. These individually wrapped axons, these endoneurium-covered fibers, are then bundled together into groups called fascicles. Think of dozens or hundreds of these thin wires being gathered together to form a thicker bundle. This entire fascicle is then wrapped in a much tougher, more substantial layer of connective tissue called the perineurium. The perineurium is a critical layer, strong and acts as a diffusion barrier, creating a tightly controlled environment for the nerve fibers within the fascicle. It helps to maintain the pressure inside the fascicle and protects the delicate axons from being stretched or compressed. But we're not done yet. The nerve itself is not just one of these fascicles. A large peripheral nerve, like the sciatic nerve, is made up of many of these perineurium-wrapped fascicles, all bundled together. The final layer of protection is a thick, tough, fibrous outer sheath that wraps around the entire collection of fascicles. This outer wrapping is called the epineurium. The epineurium is the thick, white, rubbery coating you would see if you looked at a nerve with your naked eye. It's the heavy-duty outer casing of the entire communications cable. It cushions the fascicles, protects them from external forces, and contains the blood vessels, the vasa nerva, and supply the nerve with its essential oxygen and nutrients. So you have this hierarchical structure. Axon greater than endoneurium, greater than fascicle, greater than perineurium, greater than epineurium. It's an incredibly robust and resilient design. It means that if there is minor damage to the nerve, it might only affect a few fascicles, leaving the others intact and functional. And remember what's inside this cable. It's a mixed nerve. So within these fascicles, you have motor axons and sensory axons running side by side. You have large, heavily myelinated axons for fine touch and motor commands traveling alongside small, myelinated axons for dull aching pain. You have autonomic fibers heading to sweat glands and blood vessels. It's an integrated data cable carrying multiple types of information in both directions simultaneously. This structure is also what surgeons have to contend with when they try to repair a severed nerve. A surgeon can't just sew the two ends of the epineurium together and hope for the best. For a good outcome, they have to perform microsurgery, trying to align the individual fascicles as closely as possible. It's like trying to reconnect a cut telephone cable with thousands of wires inside. It's matching up each bundle correctly to ensure the signals end up in the right place. It's an incredibly painstaking process. Understanding this intricate, cable-like structure gives you a new appreciation for what a nerve really is. It's not just a simple string. It's a sophisticated, multi-layered, highly organized biological conduit, engineered for protection, resilience, and in the high-fidelity transmission of the signals that create our reality. Throughout this entire deep dive, we have been focused on the spinal cord and the 31 pairs of spinal nerves that emerge from it. To control and receive sensation from the entire body, from the neck down. But what about the neck up? What about the incredibly complex and delicate movements of your eyes, your face, your tongue? What about the special senses of sight, hearing, smell, and taste? These functions are so critical and are located so close to the brain, they don't use the spinal cord as a middleman. They have their own dedicated VIP access lines that connect directly to the brain. These are the 12 pairs of cranial nerves. Understanding the cranial nerves is important because it helps to define what the spinal cord doesn't do. It puts our main character, the spinal cord, into its proper context within the larger nervous system. Ta-da-da! The spinal nerves are the general contractors for the body's trunk and limbs, while the cranial nerves are the elite specialists for the head and certain vital organs. They are numbered using Roman numerals from I to 12, based on where they emerge from the brain, from front to back. Let's do a quick flyby of these specialists to see how different their jobs are. Cranial nerve I is the olfactory nerve. It's purely for your sense of smell. Its fibers pass from the nasal cavity directly into the olfactory bulbs on the underside of the brain. Cranial nerve 2 is the optic nerve. This is for vision. Transmits all the visual information from your retina back into the brain for processing. Cranial nerves 3, 4, and V8, the oculomotor, trochlear, and abducens nerves, are the motor nerves for your eyes. Together, they control the 6 tiny muscles attached to each eyeball that allow you to look up, down, side to side, and everywhere in between, with incredible speed and precision. Cranial nerve V is the trigeminal nerve. This is a big, important nerve, somewhat analogous to a spinal nerve for the face. It's a mixed nerve. It provides sensory information, touch, pain, temperature from your entire face, and it controls the powerful muscles of mastication, the ones you use to chew. When a dentist numbs your jaw, they are targeting a branch of the trigeminal nerve. Cranial nerve 7 is the facial nerve. This is the nerve of facial expression. Every smile, frown, or look of surprise is generated by this nerve. It also carries taste sensation from the front 2/3 of your tongue and controls some salivary glands. Cranial nerve 8 is the vestibulocochlear nerve. This nerve has 2 distinct parts. The cochlear branch is for hearing, carrying signals from the inner ear. The vestibular branch is for balance and equilibrium, carrying information about head position and movement from the vestibular apparatus in your inner ear. The cranial nerve IX, the glossopharyngeal nerve, is a jack of all trades. It handles taste from the back of the tongue, sensation from the throat, controls a muscle for swallowing, monitors blood pressure in a major artery. Cranial nerve X is the vagus nerve. This nerve is a true wanderer, as its name implies. It is the main superhighway of the parasympathetic rest and digest nervous system. Unlike the other cranial nerves that stay mostly in the head, the vagus nerve travels down into the chest and abdomen, controlling the heart, lungs, and most of the digestive tract. It is the brain's direct line to manage your internal organs. Cranial nerve. She is the accessory nerve. Its main job is to control two big muscles in your neck and shoulders, the sternocleidomastoid and the trapezius. Shrugging your shoulders is an action of the accessory nerve. Finally, cranial nerve 12 is the hypoglossal nerve. This is a motor nerve that controls the intricate movements of your tongue, essential for speech and swallowing. So, while the spinal cord and its nerves form a vast, segmented system for the general control of the body, the cranial nerves represent a completely different organizational principle. They are highly specialized, non-segmented nerves dedicated to the unique and complex functions of the head. By appreciating their roles, we can better appreciate the specific, monumental task assigned to our hero, the spinal cord, to be the master and commander of everything from the shoulders to the toes. For centuries, a diagnosis of severe spinal cord injury was effectively a life sentence of paralysis. The tools to intervene were limited. The biological reality of the non-regenerating central nervous system seemed an insurmountable wall. But we are now living in an age of unprecedented scientific and technological advancement, and that wall is beginning to crumble. The future of spinal cord research isn't science fiction anymore. It's happening in laboratories and clinics around the world right now. One of the most electrifying frontiers is the development of brain-computer interfaces, or BCIs. The concept is both simple and breathtakingly complex. If the connection from the brain to the muscles is broken at the spinal cord, can we create an electronic bypass? BC is aimed to do just that. This involves implanting a small array of electrodes onto the surface of the brain's motor cortex to listen in on the neural signals of intended movement. Sophisticated computer algorithms then decode these signals in real time. What can we do with these decoded thoughts? In early systems, they were used to control a cursor on a screen, or a robotic arm. A person could think "move arm left," and the robotic arm would move left, but the technology is rapidly advancing. Researchers are now using these decoded brain signals to control a functional electrical stimulation FE system. FEs involves placing electrodes on the skin over a person's paralyzed muscles or implanting them directly. The BCI bypasses the injured spinal cord entirely, taking the thought from the brain and translating it into a pattern of electrical pulses that artificially contract the person's own muscles, allowing them to, for example, open and close their own hand. It is, in essence, a thought-controlled electronic nervous system. We also talked about epidural stimulation, using an implanted device to wake up the spinal circuits below the injury. The next generation of this technology is combining it with BCs. The brain interface can detect the intention to walk, which then triggers and modulates the spinal cord stimulator in a way that helps to generate a coordinated walking pattern. It's about restoring the link, re-establishing the conversation between the brain and the spinal cord's own local intelligence. On the biological front, the attack is multi-pronged. Stem cell research is a major area of focus. The idea is to transplant stem cells into the site of the injury. These cells have the potential to perform several jobs. They might differentiate into new neurons to replace the ones that died. Or, perhaps more realistically, in the short term, they could become the support cells that help create a more permissive environment for healing, releasing growth, promoting factors, and reducing the inflammation that leads to the glial scar. Clinical trials are ongoing, and while it's a slow and careful process, the potential is enormous. Simultaneously, scientists are working on ways to coax our own existing neurons to regenerate. This involves developing drugs that can overcome the inhibitory signals in the central nervous system. If we can block the stop-growing signals from the myelin and the glial scar, we might be able to unleash the axon's own innate, but suppressed ability to regrow across the injury gap. Other researchers are experimenting with bioengineered scaffolds, tiny biocompatible structures that can be implanted to create a physical bridge across the lesion for axons to grow along. Gene therapy is another avenue being explored, using harmless viruses to deliver genetic instructions to nerve cells, telling them to produce more growth factors or to become more resilient to the secondary damage cascade that follows an injury. There is no single magic bullet on the horizon. The future of treating spinal cord injury will likely be a combination therapy, an advanced surgical procedure to stabilize the spine, and clean up the injury site. Followed by a cocktail of neuroprotective drugs to limit secondary damage, then perhaps stem cell transplant or a scaffold to promote a healing environment. And finally, a long-term regimen of intensive physical therapy combined with a BCI and epidural stimulation to retrain and reactivate the surviving neural pathways. We are moving from an era of simply managing paralysis to an era of actively pursuing recovery. The work is built upon the foundational anatomical and physiological knowledge that we've been exploring. By understanding every tract, every cell type, and every chemical signal, we are learning how to intervene, how to repair, and how to restore hope. The future is about rebuilding the bridge. Close your eyes. Now, hold your hands out in front of you. Touch your 2 index fingers together. Now touch your left thumb to your right earlobe. Chances are, you did that with relative ease and accuracy, without ever opening your eyes. Have you ever stopped to think about how utterly remarkable that is? How does your brain know with such precision where your body parts are in space? How does it know the angle of your elbow, the rotation of your shoulder, the flexion of your wrist, all without visual input? You aren't consciously calculating these things, yet you have a constant real-time, 3-dimensional sense of your own body. This is proprioception. It is often called our secret 6th sense, and it is every bit as important as sight, sound, or touch. And the spinal cord is its primary conduit. Proprioception is the sensory system that gathers information from our muscles and joints. The receptors for this sense are not in the skin, but are woven into the very fabric of our musculoskeletal system. One of the key players is a sophisticated little structure called the muscle spindle. These are tiny, specialized muscle fibers that are wrapped in sensory nerve endings and are scattered throughout all of our skeletal muscles. They lie parallel to the main muscle fibers. Their job is to detect changes in muscle length and the speed of that change. When your muscle is stretched, the muscle spindle is also stretched, and it sends a signal back to the spinal cord. The faster the stretch, the faster it fires. This is the receptor that is activated when a doctor taps your knee with a reflex hammer. The tap stretches the quadriceps muscle, activating the spindles and triggering the reflex arc. The other major player is the Golgi tendon organ. These receptors are not in the muscle itself, but in the tendons that connect the muscle to the bone. Their job is to detect muscle tension or force. When a muscle contracts and pulls on its tendon, the Golgi tendon organ is squeezed, and it fires off a signal. It's like a tiny strain gauge, constantly reporting back how hard the muscle is pulling. So, at any given moment, your central nervous system is being bombarded with a torrent of proprioceptive data from thousands of muscle spindles and Golgi tendon organs all over your body. The bicep is currently at this length and is contracting with this much force. The hamstring is stretching at this rate, as the ankle joint is at this angle. What happens to all this information? It travels up the spinal cord in 2 main high-speed pathways we've already met. A huge portion of it travels up the spinocerebellar tracts. This is the unconscious pathway. This data goes directly to the cerebellum, the brain's great coordinator of movement. The cerebellum acts like a comparator. It receives a copy of the motor plan from the cerebral cortex. This is the movement we intend to make. It receives a real-time feed of proprioceptive information from the spinocerebellar tracts. This is what the body is actually doing. It then compares the intention with the reality. If there's a mismatch, if you're stumbling, or the movement isn't as smooth as intended, the cerebellum instantly calculates the error and sends corrective signals to fine-tune the movement on the fly. This is why you can walk on uneven ground or catch a ball without consciously thinking about every little adjustment to your cerebellum using unconscious proprioception. The other portion of the data travels up the dorsal columns, the same pathway that carries fine touch. This is the conscious pathway. This is the information that goes to your somatosensory cortex and gives you your conscious awareness of your body's position. This is how you knew where your finger was. To touch your nose with your eyes closed. Without proprioception, movement would be a clumsy, chaotic disaster. People who have lost their proprioception due to nerve damage have to constantly watch their limbs to know where they are. They can't walk in the dark. Simple tasks like buttoning a shirt or lifting a cup become monumental challenges because they coo and feel how their muscles are moving or how much force they're reapplying. They might crush the cup because they can't sense the tension in their grip, Proprioception is the silent, unsung hero of all coordinated movement. It is the constant stream of self-awareness that allows our brain to guide our body through a complex world, and the superhighways that carry this vital, body-defining information run right through the heart of the spinal cord's white matter. Pain is a universal human experience. We spend our lives trying to avoid it, yet it is one of the most important signals our body has. Pain is a warning system. It is a biological alarm that tells us something is wrong, that tissue is being damaged, and that we need to do something about it. It's a vital survival mechanism. But pain is not a simple, monolithic sensation. It's a complex, multifaceted experience. And the spinal cord is the first and most important place where this critical signal is processed and modulated. The journey of pain begins, as we know, at receptors in the periphery called nociceptors. But there isn't just one type of pain fiber. There are two main types of nerve fibers that transmit these alarm signals, and they are responsible for the two distinct qualities of pain that we feel. First, there are the adelta fibers. These are relatively thin, but are myelinated, which means they can transmit signals fairly quickly. Adelta fibers are responsible for what we call fast pain, or first pain. This is the sharp, stabbing, well-localized pain you feel the instant you stub your toe or get a paper cut. It's the initial ouch that makes you immediately withdraw from the source of injury. Its job is to get your attention right now. Second, there are the C fibers. These fibers are even thinner and are unmyelinated. This lack of myelin means they conduct signals much more slowly. CI fibers are responsible for slow pain or second pain. This is the dull, throbbing, aching, burning pain that sets in after the initial injury. It's the lingering soreness of a bruise, or the constant ache of a headache. This pain is less about immediate withdrawal and more about reminding you that an area is injured, needs to be protected while it heals. So, when you injure yourself, you often feel that double sensation. A quick, sharp shock, followed by a slower, spreading ache. That's your adelta fibers reporting in first, followed by the delayed arrival of the signal from your C fibers. Both types of fibers travel into the spinal cord through the dorsal root and arrive at the dorsal horn of the gray matter. And this is where things get really interesting. The dorsal horn isn't just a passive relay station. It is an active processing center, a place where the pain signal can be turned up or turned down before it is ever sent to the brain. This is the basis of the gate control theory of pain. Imagine a gate for pain signals in the dorsal horn. When the gate is open, pain signals from the adelta and C fibers can pass through, travel up the spinothalamic tract to the brain, and be perceived as pain. When the gate is closed, those signals are blocked or dampened. So what controls the gate? Other incoming sensory signals do. The large, fast, myelinated fibers that carry information about non-painful touch and pressure, the ones that travel up the dorsal columns, so send little branches to the dorsal horn. When these large fibers are activated, they tend to close the gate for the pain signals. This is the neurological basis for a behavior we all do instinctively. When you bang your shin, what's the first thing you do? You grab it and rub it vigorously. By rubbing the area, you are activating those large, fast touch and pressure fibers. Those signals rush to the spinal cord, and by activating inhibitory interneurons in the dorsal horn, they effectively close the gate on the slower, weaker pain signals coming from the C fibers. The touch sensation literally overrides the pain sensation, right there in the spinal cord. This is also the principle behind TENS units transcutaneous electrical nerve stimulation, which use electrical pulses to stimulate the large sensory fibers and provide pain relief. The brain can also control this gate. Descending pathways from the brainstem can travel down to the dorsal horn and release powerful, naturally produced painkillers like endorphins and enkephalins. These are the body's own morphine. During times of extreme stress or intense focus, the brain can effectively shut down the pain gate, allowing you to perform amazing feats without feeling pain until later. This is why an athlete can play through a serious injury only to collapse in agony after the game is over. Pain is not a simple stimulus response pathway. It is a dynamic, plastic, and highly modulated experience. The spinal cord, specifically the dorsal horn, is the first and most critical battleground, where the signals of tissue damage compete with the signals of touch and are influenced by the commands of the brain, all to determine the final message that will become our conscious perception of pain. We began this journey with a simple request. Wiggle your pinky finger. And now, almost 20,000 words later, I want you to do it again. But this time, see it for what it is. See the thought. Born in the motor cortex, a spark of intention in a universe of neurons, see it cascade down the colossal corticospinal tract. A lightning bolt of command traveling through the brainstem, crossing to the other side in the pyramids, and plunging into the white matter of your spinal cord. Picture it arriving in the cervical enlargement, that bustling hub of the gray matter butterfly, handing off its message from an upper motor neuron to a lower motor neuron. See that final command flash out the ventral root, join the great braided network of the brachial plexus, and race down a peripheral nerve, a complex, multi-layered cable running through your arm. Imagine it arriving at the neuromuscular junction in a tiny muscle in your hand, releasing a puff of acetylcholine that tells a muscle fiber to contract. And as it does, feel the proprioceptors, the muscle spindles, and Golgi tendon organs, instantly firing back reports. The muscle is shortening. The tendon is under this much tension. See that data stream back up the same nerve, in through the dorsal root, and ascending the dorsal columns and spinocerebellar tracts. It's providing the real-time feedback that makes the movement smooth and controlled. Think about the structure that made all this possible. A fortress of 33 vertebrae and their shock-absorbing discs, the triple-layered embrace of the meninges, floating in its bath of cerebrospinal fluid, the intricate geography of the gray and white matter, processing and transmitting signals at incomprehensible speeds. Remember the spinal cord's other lives? Here its role as the emergency dispatcher, executing life-saving reflexes before the brain even knows there's a problem. Its job as the silent automatic pilot, managing your heart rate and digestion through the autonomic nervous system pathways hidden in its lateral horns. Recall the invisible map of dermatomes laid across your skin, a diagnostic blueprint that connects every patch of your surface to a single segment of this central cord. We have seen what happens when this marvel of engineering is broken by trauma or eroded by disease. We have explored the hope offered by science, the quest to bypass, to repair, and to regenerate this irreplaceable lifeline. We have journeyed from its embryonic origins as a simple folded tube to its potential future, intertwined with the electronics of brain-computer interfaces. The spinal cord is the great intermediary, the ultimate go-between. It is both a servant to the brain and a master of its own domain. It is tougher than bone in some ways, and more delicate than a spider's web in others. It lives in darkness, tucked away out of sight, and, most of the time, out of mind. Yet it is the conduit for nearly every sensation that makes our world real and every action we take to shape it. It is the unsung hero of your nervous system. The hero in plain sight, hidden within your own backbone. So the next time you wiggle a finger, the next time you take a step, the next time you feel the warmth of the sun on your skin, take a second. Acknowledge the miracle. Acknowledge the silent, tireless, brilliant work of the information superhighway within.